So, welcome back to the 25th class of the 5th week. So, today we will talk about SPR. So, last 4 class we talked about all the recognition elements, and now we are back on track. This is something I was thinking that it is a good idea to expose all of you to these production technologies, which are otherwise being taught in most of the core biology courses. But since all of you are from varied background, I felt it that I exposed you to have a basic understanding. I never made an attempt to go extremely deep into the details of it, because you don't need for that. And if you need, I can always suggest that you go through books by QB and other books on immunology, which used to be our regular textbook. Go through them, you'll figure out. But the basic fundamental understanding, whatever you need, has been covered in the last 4 classes about the recognition element in terms of protein molecules as a recognition element, nucleotide as a recognition element, fast display technology, hybridoma technology, then production of SC, FBAs, and using peptides for binding of the nanomaterials in the fast display, and so on and so forth. So, now we will move on to the signal generation devices, which is SPR. So, as you could see, this is where we are. We have already talked about QCM. So, now let us move on to SPR. So, here we are. We finished this. Now, aptamers, we did the aptamers. Now, here it is. So, this is our lecture number 25th, surface plasmon resonance. So, what these technologies are when we talk about from the biosensing perspective. So, there is an antigen in the form of a toxin, form of a protein, in the form of a spores, in the form of a cell, and you have a recognition element which binds to it, right? So, you have to understand this binding. When there is a binding, there could be electron transfer. If there is electron transfer, then you can quantify it using electrochemistry, right? Or when there is electron transfer, there you can quantify it any other charge transfer mechanism, or because of the binding there is a change in weight, quartz crystal microbalance, there is a change in the topography, AFM, there could be a change in some kind of surface property of the material where this binding is taking place. And today what we will be talking about is one such technique called SPR, surface plasmon resonance, where it's a surface change. Property of the surface is altered because of the binding between antigen and antibody. Okay, so it's a surface technology, surface science, surface chemistry, precisely. Okay, so the study of molecular binding process is the key aspect to many fields of research, from life sciences to environmental safety. Determining which molecules interact, how they interact, and why they interact can ultimately lead to more effective drugs, higher performance material, cleaner air and water quality, and much more. Several technologies exist that may be utilized for such molecular binding studies. ELISA, QCM, we talked about this, and ITC. However, few encompasses as many advantages as surface plasmon resonance or SPR. SPR enables high sensitivity, label-free detection. You do not have any label for, do not need any kind of label for this detection. Real-time change when the antibody and the antigen binds. Low volume sample consumption, extremely low volume of sample is needed. Quantitative evaluation, so you can give a number to this evaluation, quantify. So, you can compare. When it's quantifiable, then it is comparable. Anything which is qualitative is a bit challenging to quantify. You cannot give it a number, it's a quality. So, you cannot say so and so more good or less good unless the good has a value. This bad, that bad, these are words which does not have any numbers. Without a number, and you cannot really understand this. So, one of the way any molecular interaction is, will be able to quantify the interaction. Okay. Determination of kinetic rate constant. Furthermore, SPR is easy to perform and can be a cost effective solution. Okay. So, how really SPR looks like? Principle of SPR detection, intensity profile and shift of the SPR angle. So, when a light beam impinges onto a metal film at a specific resonance angle, the surface plasmons are set to resonate with light. This resonance results in absorption of light. In the widely used Plasmon configuration, a beam is focused onto a metal film. The focused light provides a range of incident angle, and the reflected beam will cover the same angle range, while the projection of the beam forms a band. When SPR occurs within the spreads of angle, a dark line will appear in the band. An intensity profile of this band is plotted against the range of angle as shown in the figure. So, here what you see is the incident light and the reflected band. Is the reflected band is coming through. Okay. And in the reflected band, you see something like this. And if you look at the next picture, this will make more sense. A light is beamed upon a metal film through a prism, and the reflected light, so here you have the prism through which it is coming, reflected image shows a dark line due to SPR. So, surface plasmon resonance is a phenomena. This part in the red I have mentioned. When polarized light hit a metal film at the interface of media with different refractive indices, SPR technique excite and detect collective oscillation of free electron known as surface plasmons via Plasmon configuration, in which light is focused onto a metal film through a glass prism and the subsequent reflection is detected. So, now when you put a light is beamed upon a metal film through a prism, putting a light beam out here shows a dark line due to SPR. So, you observe a dark line in the reflected image, there is a dark line out here. Now, this dark line configuration actually changes. How it changes is the catch, and that dark line is originating because of, as you mentioned out here, SPR technique detect collective oscillation of free electrons via Plasmon configuration, in which light is focused onto a metal film through a glass prism and a subsequent reflection is detected, and that reflection has a dark band. But that dark band will change if there is some kind of molecular interaction happening on the surface of the metal, because that alters those free electrons which are moving on the surface. Okay. So, now the intensity profile of the reflected beam. So, this is the intensity profile of the reflected beam, exhibit a dip or minimal intensity at the resonance angle. So, there is the dip in the intensity which is happening. An SPR experiment measures the position and shift of the dip, the angle shift upon molecular adsorption, and this shift represents the adsorption kinetics when plotted as a function of time. So, here is this shift, this angular shift, and if we try to get a better picture, here I could show you it much better. I'll come back, something like the dip angle, this shift. This dip happens because when there is a binding event which is happening. Now, coming back where we started. So, here you have a beam which is passing through the prism, is reflected on the surface. Here you have a lot of free electrons which are getting generated, and the reflected light creates a band. Okay. Now, say for example, there is some event, molecular event happening on the surface. These molecular event alters these free electrons, the configuration, and that is called the Kretman configuration. These alteration of these free electrons of this free electron shift this band either here or either here. This shift in position of this band is what the SPR signal is, and you can actually quantify how much interaction has happened on top of the surface out here. So now if you follow this picture, it will make more sense. Here actually the binding is taking place. Here you have the ligand, you have the metal film where the free electrons are hovering around or moving around, and here is the interaction which is happening between the ligand and the biomolecule. So say for example, if this is your antigen, imagine, and this is your say antibody. So this antigen antibody reaction could be measured in real time. You're exactly seeing the interaction because you see a shift in the intensity profile out here. Now, if you move to the next slide, the excitation of surface plasmons result in a dark line in the reflected beam, and the angular position of the dark line shift as the molecular binding event takes place. Incident light, reflected light, and here is the band, original position of the band. Now, this position shifts when there is a binding of these biomolecules which are happening. So, in other words, antigen represented by AN interact with antibody AB. This interaction leads to this shift or the angular shift in the SPR at a certain incident angle or resonance angle. This is the resonance angle. The plasmons are set to resonate with the light, resulting in absorption of light at that angle. This creates a dark line in the reflected beam shown in figure. This part is of extreme importance for you to understand. Again, I am repeating, at a certain incident angle or resonance angle, at resonance angle, the plasmons are set, plasmons which are the free electron on the metal surface. These are the plasmons, resonate with the light, resulting in, so they resonate with the light, light is here. So, these electrons out here are resonating with the light. There is a resonance phenomena which is happening at the resonance angle. That's why it's called the resonance angle. To resonate with the light, resulting in absorption of light at that angle. And because of the absorption of light, it generates a shadow, and you see a dark line. This creates a dark line in the reflected beam shown in the figure. So, as long as this particular part is clear to you, everything about SPR will be clear to you. Now, this dark line, there's a shift in this dark line when there's a binding happen on the surface out here, because this alters the resonance between these free electrons and the light which is falling there. And this shift is what you are measuring or quantifying out here. So, if we talk about the SPR event, SPR scanning angle response, SPR causes an intensity dip in the reflected light at the sensor surface. A shift in the curve represents molecular binding. This is the shift we are talking about, the arrow I showed you in the beginning. So, if you look at this image where I could not really show you much more cleaner out here, you see there is a shift, but this shift is being further magnified and shown in that next image. What I am coming is out here. So, if you look at it, so this is the angular shift which is happening. One second, yeah. So, this is the angular shift, shift in reflection intensity. So, the dip angle is changing, it is shifting like this, either way whichever you look at it. Okay. Now, the angular shift versus time provides a good study of binding kinetics. The reverse process of molecular dissociation can be studied in a similar way. So, you can study the association and dissociation, because this thing will shift either this way or this way. It is a a reversible process, and it's a probe-free process, mind it. You do not have to use any kind of a probe like fluorescent probe, this probe, that probe. It is simple molecular interaction. So you have less noise. You do not have to add something else into this game. You understand that dark line contains a wealth of information the resonance angle can obtain by observing a dip in SPR reflection intensity, a shift in the reflectivity curve. Figure represent a molecular binding event taking place on or near the metal film or a conformational change in the molecular bound to the film. By monitoring this shift versus time, researcher can study molecular binding event and binding kinetics without hassle of labels. So, as I mentioned, it is a label-free technology of molecular recognition. And the best part, what I like about SPR is how you can do a reversible way. Say, for example, when you talk about reversible, say, for example, you have these ligands to which these biomolecules are binding. Now, say, for example, you put a floating ligand on top. So, what will happen? This floating ligand will bind to them and they will flow it out of the system. So, simultaneously, we will see a reverse angular shift on the surface because there is no more binding, and the conformation of those free surface plasmons or those electrons, which are, as we mentioned, the surface plasmons are, again, let me repeat the definition. Surface plasmon resonance is a phenomena that occurs when polarized light hits a metal film at an interface of media with different refractive indices. SPR technique excite and detect the collective oscillation of the free electron known as surface plasmons via Kretschmann configuration, in which light is focused onto a metal film through a glass prism and the subsequent reflection is detected. Okay? So, this real life probe-free dynamic process, reversible process makes SPR one of the very, very profound tool of interaction between ligand and its target. Okay? So, in terms of this profile is often used in a typical SPR experiment to indicate that a metal film or a solution above the metal film matches the SPR resonance condition and the apparatus is set up properly. However, the actual measurement of molecular adsorption kinetics is only related to the shift of adsorption SPR dip corresponding to SPR angle change. One has to sacrifice the resolution of measurement by acquiring the whole intensity profile curve and comparing them to find the shift of the dip, which is the minimum one. Now, with this, we covered one of the major label-free technique of detection of ligand to biomolecule binding. Now, if you go back to the picture where we moved out in terms of the recognition element, which will give you a better idea about where we started this class, is out here. One, yes. So, now think of this. These molecules, all these different fragments, peptides, aptamers, these binding with their targets, vegetative cells or spores and DNA, could all be evaluated using SPR. Now, you realize where all these things are linking up together. You can understand without using any label, because when we are talking about using label, we are talking about some kind of a fluorescent probe, we are talking about colors, we are talking about DNA amplification. Of course, electrochemistry is much more label-free system, but any system where there is a charge transport involved, where there is an alteration of charge moieties, say electron or protons or some other charge moieties, and if you could detect them, they give you lesser noise. So, you have to realize any biosensor, whatever you wish to develop, whatever areas you want to devote, one of the challenge is always the noise, signal to noise ratio, and cutting down on signal to noise ratio is not an easy job. It takes hell of a effort to cut down signal to noise ratio. So, in that context, if we talk about the SPR, as a technology, it is one of the very profoundly superb technology in terms of its specificness and in terms of its binding interaction. But having said this, you have to realize these kind of setup requires a lot of protection from the surrounding noises. So it means they have to be on a vibration isolation, they have to be ensured that the interaction, and you need very extraordinary good optics. So if you look across the world, there's a lot of investment is happening at the level of universities and techno schools on optics school, because you really need quality optics for these making these kind of detection. You need extremely good people from light physics or people who have worked with light and optics physics, optics engineering to develop these kind of devices. So you realize that on one hand you have to understand how you produce the recognition element, other hand you have to understand how they bind, the kinetics and the chemistry behind it. Other hand you have to detect how you can make those detection of those interaction. So the whole design field of biosensor design is a teamwork. While you may not need to be an expert in the area, but you need to understand how you can optimize these interactions, how you can read these interactions, how you can make these interactions noise free and much more user friendly. So you have to have a front end, you have to have a back end, you have to have a groundwork of productions, and you have to have a team of engineers, designers, chemists, biologists, immunologists, physicists, and packaging. It's a very unique field, and I'm pretty confident that in the years and decades to come, there will be a lot of jobs which will be generated in these areas where a lot of work has to be done, where we'll be able to have these as tabletop SPR detectors, almost a small chip SPR detectors, so on and so forth. So with this, I will close the class, and then next week we'll start with LIF assays, and then we'll move to the electrochemical assays, and slowly we'll keep learning about the newer and newer developments. Thanks a lot.